All right, guys, this is section 3.2, and we're going to be talking all about parent functions, and therefore also eventually what I call child functions. It's supposed to be a T. Functions, okay? And I forgot to put my ICANNs on a different slide, so here they are, and I scribbled them quickly. I can graph parent functions, and then I want you to be able to describe transformations of the child function. So those are your two things for today. And then I did attach this worksheet to today's thing, so if you would rather print this off, you can have it, but there's no reason you can't do this in your notebook with graph paper. And you guys know where the graph paper is in the classroom. It's up against, on the radiator, against the windows right now. And then the last thing that I need to tell you is I will always provide the parent function tables. So I will always give you the parent function tables. And these are things that you could, at this point, probably just stop listening and go ahead and fill out on your own. I'm going to do my best to fill them out. So this first one is a linear function, y equals x. And I gave you the x's, and the y's shouldn't be too bad either. You should be able to get them filled out. So again, I gave you, sorry, I had to pause, I had to move rooms in my house. Let's see if I can zoom in on this a little bit so I can do better. If I give you liner, that is not how you spell this. Linear should be what you're typing in here. Linear. Oh, well, let me erase that. Perfect. And linear is the word you should use. When you're doing linear, it's a line. You guys know this one already. So plug in -3, get out -3. Plug in -2, get out -2. So where am I getting these numbers? Again, I will always give them to you. I will always give you this table. Okay, you should be able to come up with this table on your own. And please, when you're graphing these, make sure that you are graphing these on a piece of graph paper and you label your scale appropriately. It will really help. And I usually say to put like 3 dots. Do as many as you're comfortable with. I'm going to find out here if I have a line tool. I don't know if I actually do. Oh, that is not what I want to do. Okay, I definitely don't have a good line tool, or if I do, I just don't know how to use it. So I'm going to do my best to draw this in. You guys should use a ruler if you can. Okay, and your line extends past the dots that you drew. It's not a dot to dot, it's a line, and it extends in both directions to infinity. The domain, usually we won't talk too much about the domain, but in this, we'll just talk a little bit about what kind of numbers can you put in. The numbers that you can put into this are all real numbers. This is the symbol that means all real numbers. Okay, so that's it for linear, the parent function linear. Move over here now to, whoa, didn't know you could do that. I'm going to move over here. I'm not going to do anything. I need to somehow bring these together. Onto x cubed. This is a cubic function. So I need my pen tool. Okay. When you cube a negative number, you get a negative answer. So -3 cubed is like saying -3 times -3 times -3, which will give you -27. Now, of course, this isn't on our graph, and that's okay. I'm going to generate the rest of these numbers, and at this point, I do just know them, and you'll probably start to just know them too. I'm going to just graph the best I can with these few points that I can graph right here in the middle, since I can't graph 3 and 27. So 0, 0, 1, 1, and then 2, 1, 2, 3, 4, 5, 8, and then same -2, 8. And what this kind of looks like is, and you can graph this on Desmos if you'd like some help too. Oh, I missed that point. I should have put it on there. It kind of looks like people say it kind of looks like a sideways S, so it doesn't have as much of an inflection when we just have regular. It kind of looks like this, but again, you're just going to do your best, make it look the best you can. All right, square root is the next one that we are going to do, and I hope that you notice that this table is a little bit different because when I pick my x's, I strategically pick x's that would be whole numbers when I took the square root of them. And that's just for ease, because I know that the square root of 0 is 0, and 1, 2, and 3 will be my answers here. This domain part is kind of where this falls in, and it's different. I can only pick real numbers that are greater than or equal to 0. When we talked about this with radical inequalities, that part underneath the radical has to be bigger than 0. So it's important that we're not picking negative numbers as our x's. And I also picked really easy numbers that would give me whole answers. So when I plot these points, 1, 2, 3, and this should look like half of a quadratic tipped on its side. Okay, so that's what that one kind of looks like. I'm going to keep moving on. Pause as you need to. Make sure you have all of these parent functions. This I would just call the square root function. I'm having trouble with my pencil today. Function. This was supposed to be an R and a T. Square root function. Okay. Number 5 here. This one I'm going to do. This is the absolute value function, and I think you guys remember that. An absolute value forms a V shape, and absolute value means always positive. So when I plug in -3, I get out +3. -2 gives me +2, but then when you plug in positive numbers, you don't switch the sign to negative, it just stays positive. So if you had your ruler still out, you would draw this in and hopefully get a nice V-shaped. I can again put in all real numbers. I only get out positive numbers, but I can put any in. Make sure it's not U-shaped and it is V-shaped. I don't actually know the name of this one. I know what it looks like, and it's really difficult to draw, so I'll do my best. First thing I'm going to write in here, and again, draw on Desmos if you'd like. I can't put in 0. 0 would make this undefined, so there will be nothing at 0. When I put in -1, I get -1, and when I put in +1, I get +1. The rest of my points are going to be fractions, which are really hard to graph on this little thing. So at +1, 1, there's a point, and at -1, 1, there's a point. Now, this one is kind of like a two-sided graph. I showed you this one yesterday when I said this would be a good graph that is odd. This is an odd graph because you could give it a turn and it would be the same. What happens is these keep getting closer and closer and closer and closer to the x-axis, but they never touch. So even though my picture is really bad, that's what happens. The domain here is all real numbers except 0. I can't plug 0 in. All right, we're down to our last two. This one is the equation of a circle. And the radius of this circle is 5. And I know that from this number right here. And so what this table is basically trying to do is, like, when you plug in 5, you get 0. Plug in 0, you'll get 5. And it kind of looks like this. But what it's really giving you is, I like to call it the edges of the circle. So 5 over, be here, 5 down, 5 over here, and 5 up. And these would be the edges of your circle. I think I have a circle tool. Wonder if I could make a nice circle. Oh, kind of. Except for it's not hollow in the middle. All right, so you could do a better circle than I can probably, even with my circle tool. Why can't I fill in the inside? I should probably, like, do these things like before I try to, give a lesson on Schoology, and then, be confused as to why, I don't know how to use my tools appropriately. No fill. Can I do that? Sorry guys, I'll stop now. All right. So anyway, you're gonna make a circle. The thing about the domain of a circle is that when you are, thinking about this, what numbers can you put in? The domain is kind of like your x value left to right. The domain is all x's between -5 and +5, because I can only go between, like, here and here, which goes from -5 all the way to +5. So the domain of a circle is a little bit different. Okay, the last one on my list is this one. Hopefully you remember that this one is the round down function. We've seen this one before. Or the floor function, meaning that whatever number I choose rounds down to the nearest whole integer. And this is on Desmos if you want to check it out. So all of these numbers, any of these, I'm getting as close as I can to 1. I'm going to get close, 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 and I can't quite make it. And I can't get to 1 until I actually pick 1. So all these numbers round down to 1. I'm getting as close as I can to 2, and I can't get 2 until I pick 2. Okay, so the domain here is all real numbers again. I can put in whatever I want, but remember, I only get out these weird little, like, barbells where it's a closed circle on the left and an open circle on the right, and a closed circle on the left and an open circle on the right, and closed on the left, open on the right, and kind of makes a staircase like this. This is it for graphing, but we have a page of notes that talks about how to describe transformations. So if, like, anything was the most important, it would be to maybe, like, put this on a separate page. You've got all these graphs. These are good. You need these. You're going to be transforming these, but I also need you to be able to describe transformations. All right, so this table is really important, but I made a typo on this, so don't copy this bit down. I'm going to change it. Okay, vertical. This is what you should write down on everything. Vertical, and then parentheses. Then inside parentheses, you're going to write horizontal and keep them in the parentheses. And this is my hint to myself all the time, that whatever happens outside is a vertical shift, and whatever happens inside is a horizontal shift. So inside, this is going to be horizontal because it's inside. Okay. What I've got is, this is going to flip or reflect. And since it's going horizontally, I always think about it like this. Horizontal is left to right. So I'm going to flip over, oh, that's the y-axis. Okay. And when it's on the outside, this is going to be like a vertical move. This is going to be a vertical flip or a reflection. So flip over. And then again, I think about this. If I'm moving vertically, I'm moving from top to bottom. That's over my x-axis. Okay, when you add a number, if you add a number C, you're going to shift up however many units that is. So there, use the letter C. If you subtract that same number surprise, surprise, you go down that many units. Okay, things get tricky now when we're talking about horizontal. Okay, horizontal always does the opposite of what you think. So when I say I'm going to add a number c inside, here, what's an example? Like this, x plus 2 squared. This one moves, oh, you're thinking it moves right. It doesn't. It moves left c units. Okay. And as we get better and better at this, we'll start seeing like what's inside, what's outside. For another example, inside would be like this. Okay. When you subtract, you move right c units. Okay, so the plus moves you left, the minus moves you right. Those things on the inside do the exact opposite of what you think they're going to do. Okay, when you have a number on the outside, so for example, 2, okay, this number on the outside here is going to stretch in the vertical direction 2 times. I'm going to write an X there. So you would say like vertical stretch by 2. This is for all numbers greater than 1. So including fractions like 5 halves or 3 halves or something like that. This one is what I generally think of as fractions, like 1/3, 1/4, but really they're just all those numbers between 0 and 1. This gives you a shrink or a compression by, I'll say like 1c units. Okay, so it's not really 1c, but it's going to be a fraction. So if I had like 1/2 the square root of x, this would be a shrink by 1/2 in the vertical direction. So put vertical somewhere in there. I forgot that. Now we're at the like opposite stuff again. So the opposite stuff inside. If I have a whole number, if I have a number like 4 on the inside, so 4x squared. This is a horizontal, and remember it does opposite, shrink by 1/c. Okay, that makes me think I need to erase this because that makes it way too confusing. This is a shrink by c units. So if I say 1/2, it would be 1/2. When I do it here, my horizontal shrink is by 1/c, meaning the shrink is by 1/4. Okay, because I got the 4. Similarly, when it's a fraction, like if I said 1/2 x like this would be a horizontal stretch by, and I'm going to say 1/c again. When I put 1/1/2, I get 2. So what am I going to ask you to do on your homework today? This probably doesn't make a lot of sense, and really, guys, that's okay, because I'm asking you to use this kind of as a reference guide right now. Instead of learning it, memorizing it, anything like that, you're just going to practice getting used to it. So I'm going to give you an equation like this, like y equals 4 x minus 2 squared plus 3. Okay, it probably won't have this many things on it, but then I need you to kind of go through and like hunt through here and figure out what it is. So I have a 4 on the outside. So here, for example, I have a big number on the outside. That's this. This should be a vertical stretch by 4. So that's what I mean by describing it. Okay. The next thing I have here, let's pick a new color. I have this minus 2 on the inside. So here's a minus on the inside. This is going to move me right 2 units. Okay, and then I have this. This is a 3 on the outside. That's this. It's going to move me up 3 units. The only other thing I might ask you to do is to give me what the parent function is. And the parent function for this is y equals x squared. That's what it all stems from. So again, guys, I'm not expecting you to like be super pros at this. I'm expecting you to kind of use this to pick out what's happening every time. We're just kind of getting used to what these moves do. Okay, your homework is posted. Make sure you read carefully what you actually have to do. Use Desmos, that's okay. We're just starting to practice.